In section 3.5, we're going to be putting together a lot of the things that we've been doing the entire chapter, but we're going to put it to an actual physical application of it. And so I want to start out with just some simple steps to help you to set up each given problem. First, anytime you're given a problem, draw a picture of what you expect. With these problems, you're going to be creating mini equations, and so it can be very beneficial to see what is going on, to see which side is where, which line is here, where an equation is. So just start with drawing a picture to represent what it's talking about. 2, identify all the given quantities and all quantities to be determined. Figure out what did each number represent. Did it represent a derivative value? Did it represent a side length? What did each number or set of information tell you? 3, write a primary equation for the quantity that's being maximized or minimized. So if it says some value is being maximized or minimized, this is going to be your primary equation that you're going to be taking derivatives of or manipulating. And it may use some known formulas, especially as you're working through the homework. 4, reduce the primary equation to one having a single variable. You may need a secondary equation. So if you're looking at a primary equation and you're like, I have 2 or 3 letters going on in here, think of another way to relate your information to something known about that shape or figure and use that to substitute into your primary equation. And the secondary equation just helps you to manipulate to a variable, not necessarily the one that you're going to be taking the derivative of. And then 5, find the first derivative of the primary equation and then find your min and max as we've done in other sections. And so this is not a ton of examples for this section, but because the problems can be a little bit lengthier, but I want to give you some application of these steps. And then as always, please reach out if you need some assistance with your individual problems. So this one says a piece of cardboard measuring 10 inches by 10 inches. So right there, I would draw me a cardboard that's 10 by 10, a square. You can see I already have kind of a sketch going over here to the side. It's formed in an open top box by cutting squares with side length from each corner and folding up the sides. And so the fact that it said cutting squares helps you to know that it is an X by X square that is being cut. Find the value for X that will maximize the volume. So that right there is telling you that's going to be your primary equation. So I'm going to say volume of a box, and we should all know this, is length times width times height. Now, length, width, height, volume, that's 4 different letters. I needed to get it down into some 2 letters, such as like an XY situation. So let's think about this. If my entire square was 10 inches, and I'm taking out a little square piece here that is X by X, then each of my sides are going to be 10 minus 2X. And so what would be my length? It would be 10 minus 2X. What would be my width? 10 minus 2X. And what would be my height? Well, if I take this and fold it upwards, that would be my height of just X. So I'm going to go ahead and complete my algebra of this and multiply this together. This gives me 100 minus 40x plus 4x squared times x, and then distribute that x in there. So that gives me 100x minus 40x squared plus 4x cubed. Now then, since I want to maximize the volume, I'm going to be taking the derivative of my volume. So it gives me 100 minus 80x plus 12x squared. In order to maximize that, I'm going to find my critical numbers. Reminder, in order to find those critical numbers, you're going to take your derivative, 100 minus 80x plus 12x squared, and set it equal to 0. So I'm going to go ahead and line this up as a quadratic would be lined up so I can better work with it. And then I can see that I can factor a 4 out of this, giving me 3x squared minus 20x plus 25 equal to 0. And then this also factors. Now again, if you struggle with factoring, go back to your quadratic formula. This will be actually 3x and x. They're both minus signs, and then it will be 5 and 5. So then solving that out, you get x to be 5 over 3 and x to be 5. Now I can't have two different side lengths, so I need to think about what's going to be possible. Now this is going to be a closed interval problem because the side length, since it's just something, a physical problem, something you can see, do, touch, the smallest x could be 0. And if I were to plug 0 into this volume equation here, it would just give me an output of 0. So that would be the smallest it could be. Now I'm going to go ahead and check the 5/3 and the 5. And I need to know, like, is there a cap out on how much the side length could be? Well, what that is called the feasible domain. Let's think through this. If we have volume, actual application, cutting of the cardboard, we know that x has to be greater than or equal to 0. Because if it were equal to 0, that would mean that we are not cutting any of the sides, which, I mean, guess doesn't really give us a very good box, but that would be the smallest it can be. And then we know that it also can't be negative because I can't, add to it by making x negative. Then the other thing that we know is we know that 10 minus 2x must be greater than or equal to 0 because the side length has to be at least 0. Again, not the best box, but then it'll go up from there. Main thing is it can't be negative. So if I look at this value and I solve this simple inequality, I get 10 to be greater than or equal to 2x and then divide by 2. So x has to be less than or equal to 5. Basically, that is giving us that if we are taking that x and making it as big as possible, what is our length doing? And so we can see that our x has to be less than 5. Otherwise, we're not going to be able to fold or cut this box correctly. That being said, that means that these are going to be x has to be bigger than or equal to 0. We saw this here. And x cannot exceed 5 because we saw this here. So then if we take these values, and you remember how you work with maximizing values on a closed interval. So 0 and 5 are endpoints. 5/3 is a critical number in between them. Checking all the values, plugging right here into this volume formula, or one of these two. They're all three equivalent. But make sure you're going back into volume, not derivative. 5/3 yields a value of 74.07, and 5 plugged in gives us a value of 0. So this assures us that 5/3 is the maximum area that we can cut off in order to maximize the volume. And so it says find the value for x that will maximize the volume of the box, and that would be x equal to 5/3 inches. And so I want to walk you through this entire problem, talk about feasible domain as you go, and that gives you a cap on some of the values that you can deal with. Now, I love a good box problem, so just keep that in mind as you're working through these. Let's do another example. It is going to be a box, but let's see what happens with it. It says a box with a square base and open top has a surface area of 108 inches squared. We wish to find the dimensions of the box that would maximize the volume of the box. So let's just kind of start from the beginning. It says a box, and so I'm going to draw a box. Doesn't have to be a pretty box. But let's just get an idea of what we're working with here. It has a square base and an open top, so that means we don't have a lid on this one. It has a surface area of 108 inches squared. Now remember, surface area is like you're taking wrapping paper and wrapping the entire box. So we're going to have to use that information somehow. We wish to find the dimensions of the box that would maximize the volume. So that means that volume is our primary equation. This is the one whenever you see the word maximize, you want to be taking the derivative of. And that means surface area is just our secondary equation that's going to help us to solve for one variable. So let's first start with that surface area. And so we know that surface area of a box is going to be equal to the area of the bottom plus the area of the four sides. Now it says that this box is a square base, so let me call this x and this x. And then it did not say it was a square box, and so we're going to call the height of it h. So in order to get this surface area, the area of the bottom would be x times x, which is x squared, plus the area of the four sides. Well, that would mean 4 times x times h, because h is the height and x is the width. then we know that this is equal to 108 inches squared. And so we've kind of got an equation here going on, and you can see that it only has the two variables, which makes it work nicely. But again, this is our secondary equation. This is what we know. And so we need to now go to our primary equation, and that's going to be the one we actually use to take a derivative. And so my primary equation is going to be volume of this box, like the previous problem, which is length times width times height. We know that the length is x, the width is x, and the height is h. So that gives me x squared h. But now I have three variables. I have w, x, and h. So we're going to use our secondary equation to plug into it. X's are the thing we like to work with. And so what I want to do is I am going to take x squared plus 4xh equal to 108. And I'm going to solve for h. So I'm going to minus the x squared from both sides. That gives me 4xh equal to 108 minus x squared. Then divide by 4x. And so that gives me h equal to 108 minus x squared all over 4x. And that's going to be what I sub in for h. So I'm going to take this value and plug it in here. So I have volume equal to x squared, and instead of h, we're going to plug in that fraction, 108 minus x squared all over 4x. I'm going to go ahead and simplify that. These x's would cancel, so I get volume to be x times 108 minus x squared all over 4. And then I'm going to go ahead and distribute that x in. So it gives me a value of 108x minus x cubed all over 4. Now, we are wanting to maximize that volume. So let's go ahead and divide it once more and divide them both by 4. So I have individual terms here. So that gives me 27x minus 1/4 x cubed. So to maximize, we're going to take the derivative. Our derivative would be 27 minus 3/4 x squared. And then that is what we're going to use in order to find our critical numbers. So our critical numbers would be when our derivative is set equal to 0. So I'm going to say 27 minus 3/4 x squared equal to 0. I'm going to solve it out from there. And so I'm going to go ahead and add that 3/4 x squared to the other side. I'm going to divide both sides by 3/4. That gives me x squared equal to 36. And then square root both sides to give me x equal to plus or minus 6. Now again, let's have the discussion of a feasible domain. So with our feasible domain, remember that our x has to be greater than or equal to 0 because x is representative of a side length on the box and it can't be negative. And then we also know that x squared has to be less than or equal to 108, and that would be if the entire bottom of the box contained all the surface area. So we know that it cannot exceed the 108. And so if I square root both sides, I get x has to be less than or equal to the square root of 108. So if we go back into our volume over here and we think about our critical numbers and our endpoints, we know that it's going to be between 0 and square root of 108, and 6 would be in the middle. Again, we're not using the negative because our side length cannot be negative. Plugging into our volume function, which I'm going to go to this one right here, plugging in 0 gives us 0. Plugging in the square root of 108 also gives me 0, and I'm just plugging back into that volume formula, and plugging in 6 gives me 108. And so it says we wish to find the dimensions of the box that would maximize it. Well, if 6 is our x, coming back up here, that means we would have 6, 6, and then in order to find h, you plug 6 into your equation, solve for h, and you get a value of 3. And I know you can evaluate that. Use your calculator, be careful with your division. But this gives us that a 6 by 6 by 3 box would be the maximum volume restricted by that surface area of 108. with these problems, they are not mathematics intensive, but you do have to kind of think through what do you have, what do you know, and what can you do with it. So let's take a break from a box and let's move on to another problem. This one says, you need to reach your home as quickly as possible, but you're in a rowboat on a lake 4 miles from shore and your home is 7 miles up the shore. If you can row at 3 miles per hour and walk at 5 miles per hour, toward which point on the shore should you row? So please draw a picture to represent this. And so here's our boat. Here's us on our boat. Lovely drawing there. And we're on the water. It said you need to reach home as quickly as possible, but you're in a rowboat on a lake 4 miles from the shore. So 4 miles, and then here's our shoreline. Your home is 7 miles up the shore. So here's home, and it is 7 miles. If you can row at 3 miles per hour and walk at 5 miles per hour, to which point on the shore should you row? And so we're trying to figure out, if we extend this way, we'll call this Y, we'll call this X. We need to figure out, where do we need to land on the shoreline to really maximize our speed of our rowing and our walking in combination. And obviously we have to have both, because they are 4 miles away from shore. So at some point you got to row back to shore. We just need to figure out, do we need to row straight back to shore and just walk our way home based on how fast we can walk? Do we need to row a little bit further up the shore and then walk home? And so let's figure out what we're doing from here. If we look at this problem, we can see that it created some sort of a triangle. So we are going to use the Pythagorean theorem to find the distance to the point P that we want to get to. And so I'm going to say y squared is equal to 4 squared plus, we're going to call it x because we don't know how far up the shore we want to go, x squared. Solving that for y, I get y equal to the square root of, let's go ahead and call that 16 plus x squared. And so there's one equation that we can use to work this problem. Now, if we think about our speed, because we're trying to walk and row and get there, let's call t the total amount of time. And we know that we want to row and walk to get our time. So this would be equal to y over our rate for our rowing plus our walking time would be 7 minus x, because we know that this is the point if we just row straight to shore and then it's 7 miles to home. And so the amount we walk is going to be 7 minus x over the rate. And that's going to give us our time. So let's take this concept here, and we are wanting to maximize our time. So that's going to be our primary. But we're going to use this Pythagorean part, our secondary, in order to get all of our data to be in the same variable. So let's come back up here. And so our total time is going to be equal to, we said it was going to be y, which we have solved to be the square root of x squared plus 16. I just switched those just for general purposes. Over our rate at which it is for us to row, and it said our rate for rowing was 3 miles per hour. Plus, we're going to do our 7 minus x, which we already had, over our rate for walking, which we are walking at 5 miles per hour. So that's our time equation. I'm going to just manipulate this to make it a little bit more user-friendly. So that would be 1/3 the square root of x squared plus 16 plus 1/5 7 minus x. And so now when I come in here, in order to maximize this, I'm going to have to take the derivative. So this is going to be, let's do a little bit more algebra before we get going on that. This would be 1/3. Let's rewrite this as a 1/2 power. So we're ready to take the derivative. And then let's go ahead and simplify this up. This would be 7/5 minus 1/5 x. And that'll make our derivative rules a little bit easier and help us to work with that square root. And so now the derivative would be, bring that 1/2 down to give us a 1/6 x squared plus 16 to the negative 1/2 times the derivative of the inside, which is 2x. Let's see, the derivative of 7/5 would go away, and so then it would be minus 1/5, the derivative of that negative 1/5 x. Let's clean that up, and so that would give me, let's see, 2 over 6 would reduce to 3, x would stay on top, the square root's negative, and so we could put it on bottom. Minus 1/5. Now I'm going to go ahead and put those fractions together because I'm going to take this derivative and set it equal to 0, and be better if I had one term over here, especially if it was a fraction. So I'm going to do my fraction trick. I'm going to multiply this way to give me 5x, minus multiply this way to give me 3 square root of x squared plus 16, all over multiply this way, which would be 15 square root of x squared plus 16 equal to 0. Now the reason I would want to do that fraction trick and get it equal to 0 is because when I'm solving this out, the only time that this fraction would give me 0 is if that numerator was 0. So now I'm going to work with that. So this would be 5x minus 3 square root of x squared plus 16 equal to 0. I'm going to move this piece over here in order to make it positive. So I get 5x equal to the square root of 3, let's see, x squared plus 16. And then I'm solving from here. So I am going to square both sides to eliminate that square root. That gives me 25x squared, make sure you're squaring that 5, equal to 9 times x squared plus 16. And then work from there. So I'm going to distribute that 9, so it gives me 25x squared equal to 9x squared plus 144. Algebra is what's going to get you in this one. Minus the 9x squared. That gives me 16x squared equal to 144. Divide both sides by 16. So x squared is equal to 9. And then square root. So I get x to be plus or minus 3. That is a booger of algebra there, but hopefully you can go slow, walk through those steps. If you need assistance or you can't see where something come from, just reach out and I'll be happy to clarify or help you along the way. So looking at this, as we've talked about in other examples, -3 is not relevant for this application problem. And so we are going to be looking at 3. We know that x is representative of the amount that we are walking. And so if we go straight to home, x could be 0, that we didn't walk any. And this is our time function. And then let's talk about feasible domain for the largest one. And so feasible domain. So looking at the feasible domain, we know that x has to be greater than, oh, too many zeros there. That x has to be greater than or equal to 0 by that conversation we just had. And we know that x has to be also less than or equal to 7 because we come up here. And if we row all the way over here to the shore, then we have 7 miles maximum that we could actually walk. And so that would be 7 as the largest it could be. And so we know that we are going to have to be between 0 and 7. So again, when we go back and plug in this 0, 3, and 7, make sure you are plugging back in to your time function, whichever version of it you would like to. Plugging in 0, you get 41 over 15, which is like 2.73. Plugging in 3, we get 37 over 15, which would be 2.47. And plugging in 7 would be square root of 65 over 3, which is 2.69. Now we are wanting to minimize how far we walk. And so looking at these values, this one right here is the smallest amount of total time that we would actually travel. And so that means my x would be 3. Meaning, coming back up here, we need to row 3 miles more upshore and then we'll walk additional 4 miles. Now this one is definitely a little bit harder because now we were trying to walk quickly and we were trying to minimize our total time. We had to draw a picture. We had to pull in Pythagorean. But again, if you need any additional help in this section, either in the homework problems or understanding details from this, please reach out. I'll be happy to help you. This is kind of a culmination of everything that we've been doing.